Okay, so working? Yes, perfect. So first of all, I also want to thank Joel and Abishai for inviting me and for inviting me so many times here. It has been a long time since I started coming, and most of my projects and collaborations started here, so it's great to be one more time here. But today I am not going to talk about the CGM or spiral arms or not even about the Agora project, although the Agora project will appear at some point during the presentation. But I am going to present a new project that we have started with it started with some friends, and now it's getting more and more speed. That is the ARRAKIHS space mission. So just to start a bit about what we are going, or what we are planning to do, the idea is to study the low surface brightness universe, and if most of the people that is working here in observations use it to see these kind of pictures, knowing where you have the picture of a galaxy, you get information from the spectra, from the photometry, and basically you focus in the galaxy and the star formation within the galaxy. But if you can do some more deep observations in the surface brightness, you start seeing that the galaxies, in fact, are not just these, but there are lots of structures, lots of substructure inside the halo, as streams, or like in the previous presentation was presented, some very, very faint dwarfs. If you take a look in a deeper sample, like a larger sample of galaxies in the local universe, not talking of this very high redshift universe that has been the main topic of the conference, but again going back to the local universe, there are still many things to understand. You can see that most of the galaxies show these very nice streams, and satellite galaxies that are becoming a street, no? That from the theory is clear that this should happen. And this is basically, if we go at the magnitude of 28.5, surface brightness of 28.5, we start seeing all these kind of substructures. But we know that there is a lot more substructure than this that we cannot see if we only go to this surface brightness. And why it's so interesting to go deep in the surface brightness? Well, because in fact, if we could observe everything in the halos of galaxies, we could very easily to disentangle between the dark matter natures. For example, some tests we have done, now for the moment it's basically using theory. We have seen that here in these panels, I show you the luminosity in the V-band versus the number of galaxies or satellites you can find within 300 kiloparsecs of Milky Way size galaxy. For the cold dark matter, you have the blue line. For the different flavors of warm dark matter, you have the red line here for 1.1 kiloelectron volt and up to 4.0 kiloelectron volts. Remember that cold dark matter is about 30 kiloelectron volts. And you can see that if you go low in the magnitude, you suddenly can clearly disentangle the different dark matter natures. So this is one of the goals that we are pursuing with this mission. Also, not only counting satellites, but also with, if you look directly to the images, the difference is quite clear. Here you can see for the warm dark matter and for the cold dark matter, how not only the satellites, but also the substructure, like the shells, the streams, are a lot more defined, and you have a lot more of these substructures with the cold dark matter. So if we can go deep in surface brightness, we can really see the differences between the cold dark matter. Talking about the streams, if we go to stellar streams, we also know that if we can reach, you have now here the limiting surface brightness, if we can reach a surface brightness of about 30 to 31, we should be able to observe stellar streams in all the galaxies that we observe. For the moment, the limit we have is this one at about 28 point something magnitude, and we see that not all the galaxies show streams because we are not going deep enough. But the theory in the cold dark matter paradigm tells us that we should be able to observe lots of streams in each one of the Milky Way size galaxies. Also, talking about the streams, another proof that we can have about the nature of dark matter is that in a universe with a warm dark matter, with a very soft dark matter potential in the outskirts of galaxies, we should observe stellar streams that are smooth, very linear, with not a lot of holes, and very nice streams, and also that we should observe fewer streams than what we expect. For example, you have here this figure by Pearson 2017, in where they put a galaxy to be stripped in a dark matter halo, one smooth, one clumpy, and you can see that the clumpy dark matter halo, that is basically a cold dark matter halo, you have a lot more streams, like the satellite is a lot more stripped than in the case of a smooth potential. Also, something interesting that we could observe if we can see a lot of streams is that the streams should show breaks in the stream because suddenly having a small dark matter halo crossing the stream and destroying the stream. So we should be able to start observing also breaks in the stellar streams if we can go deep enough in the surface brightness. What do we need to make these observations? Well, we have many problems. First of all, we need resolved streams and satellites. This means that for the moment we have to be restricted on the local universe because we want to resolve the dwarfs, that the size should be about this 1.5 arc seconds. That is the resolution we can have. This also means that if we want to look at Milky Way-sized galaxies, we will need a very wide field of views or to make mosaics with the instruments that we have. For example, for a Milky Way mass galaxy that is a 30 megaparsec, we will need a field of view of 30 times 30 arc minutes. If you compare what we need with what we get from space telescopes or from the largest ground-based telescopes, basically you can see that we really would need mosaics to take a picture like this one that we are getting with a smaller telescope, ground-based telescope. No? These are the fields for the Hubble Space Telescope instruments. These are the fields, just in the same direct comparison with the field that we need for the galaxies with the James Webb Space Telescope. And in EMIR, that is one of the instruments with a larger field of view in the GTC telescope in Canary Islands, we reach 6 times 6 arc minutes. So still not good enough for the images that we are looking for. So, also, if we want to test the dark matter nature, we don't need a single observation. We need to observe a lot of galaxies to have a statistically significant sample. This means lots of hours of observation. This is completely not possible to ask for these lots of hours in the large telescopes. Not, of course, with the space telescopes. We cannot ask for 200 hours in the James Webb. So the idea is that maybe we could ask for time using maybe amateur telescopes, maybe robotic small telescopes ground-based. And this is what has been done by David Martinez Delgado in the last 15 years. The problem, but, is that the ground-based telescopes have a limitation, a big limitation, that is the brightness of the sky. That is at about 29 magnitudes per arc second. So we can really not reach the surface brightness that we want from the ground. And this is a big problem. Also because this is one of the deepest images that you can get from the ground, and you can see that the shells are barely visible. Also, the other problem is that from the ground you have the atmosphere that is perturbing you a lot, the images, and you are getting a very bad resolution. So you cannot even distinguish between dwarf galaxies that are in the halos you are observing and the background, or also some foreground stars. So this is also a big problem, the sea that we have if we're inside the atmosphere. But there is still another problem if you are inside the atmosphere. This is bad for the visible, but if you want the infrared, if you need the infrared, maybe you need the infrared, you cannot get so deep surface brightness either. So it's a lot worse with the infrared. And we need the infrared, because when you go deep in the surface brightness, suddenly a nice image like this one that you have Andromeda and all the satellite galaxies became something like that. With a lot of substructure here, that this is not streams. This is basically dust clouds in the Milky Way. This is the famous or infamous cirri that is basically perturbing all our observations and makes our life very difficult. And to distinguish between the cirri and the real stellar streams, we need colors, and we need the visible and the infrared. And this cannot be done from ground. So, if you go, this is just showing you that with colors you can distinguish. These are the cirri, the dots, and these are the galaxies. And clearly in these color diagrams, the two things are clearly disentangled. So a group of friends joined several years ago. We said that maybe we could send not a telescope, not a small telescope, but a binocular, and for the same price, or just a little more expensive, 2 binoculars to space. And this was the origin of the ARRAKIHS space mission. We proposed that to the ESA in 2021, and it got approved, and now it's just going very fast to the design of the mission. The mission is led by Rafael Guzman, that is well known also here in Santa Cruz. He was, I think, doing a postdoc here with you, David? Yes? So he was here in Santa Cruz, and he's the leader of the mission. And now, and you can see here the consortium, there is also many people in the room that is participating now in ARRAKIHS. And basically, this is some very recent news. We finally went over the phase 0 of the space mission. We are almost in the phase A, and we also got something important for a space mission, that is, we have the logo. It's not the best logo that ESA did, so ESA is not in its best time on designing logos, but still, we have a logo for the space mission. Okay, so some general properties of ARRAKIHS. This is 2 binoculars. Each one of the telescopes will have a filter. 2 filters in the visible, 2 filters in the infrared. You have here the details. For the filters in the visible, we are still thinking on which kind of filters we will be using. The idea initially was to use Euclid filters. This will happen for the infrared. But for the visible, we are now thinking on moving to the Gaia filters, just because of all the synergies we can have with Gaia, and also because Gaia has a bit wider filters. That really is what we want. We want to take all the photons we can. And also because Gaia blue filter goes a bit deeper in the blue. Okay? So, and this is interesting also for the nature of the streams. Also, this is to be discussed, the filters. And the other important thing is the resolution. We will be able to get, this is a mock image, to distinguish between dwarf galaxies and foreground stars in a quite good way. The survey, it was initially thought to be of 70 galaxies, but now we increased the number of Milky Way type galaxies that we want to observe. This will come from the SAGA survey. We can talk about the biases that SAGA has, but basically it's Milky Way-like galaxies, quite isolated, because what we want is to count satellites and streams. We don't want to have a very hard environment around the galaxies. So the idea is these 250 Milky Way-sized galaxies that are in between 25 and 50 megaparsecs. And important, we need them to be away from the Milky Way disk, and very important, away from the zodiacal light, away from the ecliptic plane. Because when you go to so deep in the surface brightness, suddenly all the shining dust in the plane of the solar system is extremely bad. So the background, the limiting magnitude, is given by the shining of the particles in the solar system. So we need to go away from the zodiacal light, from the solar system plane. This will be revisited, also the sample of galaxies, once we get more data from Gaia DR4 and also from Euclid. It's great that it has been a success, the mission for the world. It's success, the launch. The mission probably will also be, but we are waiting for the data. Okay, talking about Euclid, we are basically the small sibling of Euclid. Euclid will be reaching a 29.5 surface magnitude. We are going a lot deeper, and Euclid will also have a deep survey that will be super useful for us to test our strength and how we can really distinguish between the foreground, background, and the galaxies within the halos. And here a comparison of what Euclid will be able to do. This is the image without any kind of cut in the surface brightness, and this is cutting at 29.5. That should be what will Euclid do. And this is, in the case of ARRAKIHS, no? You start seeing many newer streams, and also that the satellite galaxies, instead of being a point source, start getting larger, so we can distinguish them from stars. And now, finishing and going to the part that I am coordinating, we are planning to produce a lot of cosmological simulations to be able to compare the observations with the different dermatite flavors. The team that we assembled is this one here. You can recognize probably many colleagues, some of them already in the room. We have been working hard in the last month to prove that ARRAKIHS will be a good mission. This is more or less the scheme of what we want to do in the next 8 years. That basically we are kind of willing to produce a very big set of cosmological models. The idea is about 40 models with different, from the Agora, selecting halos from the Agora prescriptions, with high resolution and with different dark matter flavors. And also we developed a new tool to produce mock images that will be the mock ARRAKIHS images. And here you can recognize, for example, again, the word Agora. I have to make some publicity about Agora. We really have a group that is working on making mock images from the Agora simulations that will be a key group here to produce the final ARRAKIHS luminosities. And also, you can see, I will not enter in the details on all the models that we are planning to do. The selection of the sample for the selection of the initial conditions. This is basically selecting in dynamical mass versus stellar mass from the TNG 50 models. And this will be probably the initial conditions. Also going through all the possible mass assembly histories of the galaxies. We are also planning probably to use different codes. And also, we will get 40 initial conditions from the TNG set, and also the initial conditions from Agora, taking advantage that we already have a very well-defined model with more than 14 cosmological models, comparing different codes, comparing different baryonic physics, so why not to take advantage of that, and also run the ARRAKIHS models with the Agora initial conditions and prescriptions. And this is also the summary of the models that we want to do. First, this set of dark matter only using Piketty graph, very fast, high resolution spatial and mass resolution as a first test of different dark matter nature. Then full cosmological simulations, a bit less resolution in the spatial resolution because it's computationally really expensive. The code is still to be decided. And also, and very interesting, with these resolutions we cannot reach the resolution that is needed to see the tidal streams from globular clusters. You know that the globular clusters also leave a stream of stars, but it's very thin, is about 10 parsecs or less, and this cannot be obviously resolved by these cosmological simulations. So we are going to extract the main system from the cosmological simulations we generate and do the spray particle technique that Dennis Ercal from the UK is an expert on, and injecting particles following the same potential that we will get from the cosmological simulations to see the formation of streams from globular clusters. And in different dark matter natures, no? The halos that have a lot of superstructure or less superstructure. And to end with, these are the projected scientific projects. Of course, we are starting. We have discussing it. We have many people thinking on the different things that we will be able to do with ARRAKIHS. And more important, before the ARRAKIHS is launched, remember that we are going to produce a large set of cosmological simulations that can be used also for other science cases. So we want to study the formation of stellar streams, the satellite galaxy mass function at very, very low luminosities. Very important thing is that we will have enough statistics to start really seeing if the planes of satellites, that is one of the big problems being studied now, are real or just in a statistical thing, no? This is also one of the projects we have, to study the intra-halo light that is related with the accretion rate of galaxies and also how the satellite galaxies are being stripped. Also study the solar system, the dust present in the disk in the old disk of the formation of the solar system. Also, we are thinking on a follow-up of Gaia. You know that you know Gaia very well, of course. It's a new mission that is related with Gaia that is called Gaia Near. Is now being presented to the ESA to be launched in 2050. And this mission will be the same as Gaia, but in the infrared and going a lot deeper. So we will be in the middle between Gaia Normal and Gaia Near Infrared, so to have information of specific targets, because these will be specific targets, will be interesting to have astrometry for these stars that will be in the fields that we will be observing. And finally, the many new projects that can be started using the high-resolution models that we will be producing. The idea of the ARRAKIHS consortium is to make public all the data that will be generated. And basically, that's all. So more to come in the future. We are just starting. So thank you for your attention.
No. Oh, there it is. Sorry. Very nice talk, Santi. So I didn't... sorry, Johnny Powell, Reed College. So what are the individual diameters of each of the monoculars of your binocular system? Maybe I missed that.
Well, I have here the field of view. It's not super settled yet. The size, in fact, is one of the things where we are still trying to deal with the ESA. Because as large as we can send them to space, the best, no? We will have more photons. I don't have, honestly, here now the numbers. I can look for them. But it's a small telescopes. Like I will not say a number,
sure.
because I will be wrong.
Okay,
I
thank
can
you.
talk about that later.
Hi, I'm Stephanie. How different from the current Landesindien dark matter would the dark matter have to be for you to be able to tell a difference? So like what mass of one dark matter, fuzzy, etc.?
Yeah, this depends a lot on how large the sample we can get. So as larger the sample and as deeper as we can go, we can disentangle between more and more models. For the moment, the theory is telling us that using 75 targets, we can discard or not discard up to, it was 3 kiloelectron volts. So in between 30 and 3. The things lower than 3 kiloelectron volts, we cannot distinguish.
Okay, cool, thanks.
Hi, Phil Mansfield from Stanford. So I was wondering if you were planning to make the pipeline for generating these mock images public at some point. So, for example, our group has been working sort of a lot on the impact of the galaxy halo connection on different stream formation and this sort of thing. We'd love to make predictions for this sort of mission.
Yeah. We are going to publish that. In fact, our policy is free software policy. No? In fact, for the moment, the tool that is super preliminary is already in GitHub, the one to generate the ARRAKIHS images. For the moment, with only the Euclid filters, but we're implementing now the Gaia filters. Important, it doesn't have yet radiative transfer, but what we are also producing is all the post-processing going inside the different telescopes. So everything like a straight light, the instrumental, like the PSF, everything is implemented already and the tool is ready and is also in GitHub. So this will be public soon, probably. So yeah, stay tuned. Or if you send me an email, I can just send you the link to that.
Hi, I'm Viraj. Thank you for this amazing project. It seems very cool. So a question I had. So it's from ground-based telescopes. It's known that star-galaxy separation is a big issue. So could you comment on like how this, like, with your specific mission, like how good it can do with that aspect?
Sorry, can you repeat? With what?
Oh, see, with like regarding star-galaxy separation, like because when you try to identify like these faint systems, like clusters or dwarf galaxies, at the very faint magnitude, it becomes hard to like separate stars from galaxies.
Yes, yes. We have it's one of the very big issues that we are dealing with. But the point is that galaxies have a shape, usually are not round. So in fact, if you have, although you are not resolving entirely the galaxy, you can still have like an over density of photons in the neighbor pixels. And the idea is to use the machine learning techniques to take this. And also, the other thing is the colors. So we will have 4 filters, and we are optimizing the filters to be able to distinguish that from stars. So there are many approaches that we are trying to use.
All right, we're already eating into the coffee break, so why don't we stop here, save discussion for coffee, and thank all of our speakers this morning once again.
Just a final remark.